Now we will proceed to the study of the reception of a TV signal broadcast by satellite. And this is the example and the problem we asked you to study. It's just one of the transponders in the Astra 1N satellite, located in 19.2 degrees east on the geo orbit. And we are going to select one of those channels to study. And here you have some basic data on the satellite. It's a very powerful one, 13 kilowatts of DC power. They have solar cells of about 20 meters long on each side. And the mass at the launch was 5.4 tons. And really, about half of this mass was just the fuel to attain the geo orbit and to keep a station in there, the satellite, during the 15 years lifetime of the satellite. Has a very large number of channels, and each one is fed with about this power, 134 watts, and the antennas have a size of about 2.5 meters. This is how the satellite looks. This is a real image of the satellite. Very frequently you just see artist impressions, but this is just the satellite. Here you have the body, the main body. On two sides are the solar panels. On the other two sides are the antennas folded for launch. The antennas are made of carbon fiber, and the base for this is just a Kevlar honeycomb. So those are not the metallic, nice white antennas you see in some pictures. And you need 3 or 4 antennas, depending on the satellite, to receive the signal from the Earth, and another one to broadcast onto the Earth. The satellite on top of this, it has an steerable antenna. The size is 3 by 3 meters typically, and up to 5 meters up there. Inside the body are 4 fuel tanks with hydrogen, and there are many, many thrusters around, plus a big engine on the tail, just to bring from the elliptical orbit to the geo orbit the satellite, and also to keep it stationed and pointing down to the Earth. What you see here is just thermal protection. There's plenty of thermal contacts and pipes inside with ammonia, just to bring the heat from the sunny sides of the satellite to the cold side, and also just to radiate the power generated by the satellite. And those are the solar cells folded. This is just a Kapton film backed by aluminum foil. It's not gold, although those satellites carry in their wiring and circuits about 20 kilograms of gold, each one of them. So this is really a very sophisticated industry in the way they work and they prepare things for such a long lifetime. The basic data for the satellite is listed in this slide. Here you have the reference distance to the equator. You have also the transponder power. Again, antenna gain. This is the equivalent isotropically radiated power. The transponder frequency, polarization, bandwidth. And here you have data on the standard, the coding, and the modulation. So this is just the data we talk about. And the satellite is at this orbital position, is 19.2 east, and it constantly has to be adjusted. So normally a satellite like this is maintained in, let's say, more or less on a well-defined position that may really be around 0.1 degrees of variation. That means about 35 kilometers on latitude and longitude, and about 75 kilometers on range. And in some cases, there are more than one satellite in an orbital position, so they have to be kept in there during all the time in a very well-controlled environment. And at the end of the life of the satellite, with the remaining fuel, the satellite will be just expelled from this orbit to make room for another one. So this is just a very scarce resource, so they don't want to leave there any old satellite. They send them to a cemetery, to a graveyard that is up in the sky. Here you have some trigonometric expressions to relate the receiver and the satellite. The satellite is on this line. This is the projection on the surface of the Earth. This is the radius of the Earth. This is the difference in longitude between the receiver and the satellite, is in here. This is the latitude of the receiver, since we assume that is exactly on the equator. The satellite is in there. And HS is the distance from the surface of the Earth to the satellite. And with those parameters, we can start working. The radius of the Earth at the equator is around this number, and the height, the nominal height of the satellite is this number, although we normally say that it's around 36,000 kilometers. But this is going to change slightly depending on the station where the satellite is kept. And this is just a simple trigonometric expression that will give you the distance from the Earth station to the satellite. As an example, for this satellite, where we assume that a certain moment is at this position, you can find in the web also plenty of information at any time where the satellite is. What are the predictions for the next days on the stationing of the satellite. So let's take 19.2 exact, and also for latitude 0 for the satellite, and we place the antenna in the campus, in the UPC campus in Barcelona. That means that the longitude is 2.16 east and 41 degrees north. Those are the GPS coordinates for our campus. And let's say that the satellite at this moment is at 3,500, 800 kilometers, it's roughly this number. With this expression here, we can now find the distance to the satellite, the range, and is approximately 37,900 kilometers. So that's the distance from the ground station to the satellite. And you can work, there's some apps that will give you this data, but that's the basic way to proceed. And now we have a second problem, is that we have to point the receiving antenna. To point the antenna, now you have to consider one thing, that everything is related to the local horizontal plane on where you are. For instance, if I want to place an antenna here, to me, the important plane is the horizontal plane, is the floor of this room. So now I have to look south, and from this plane I have to go up until I point to the satellite. And this is just the elevation angle, which is the complementary of the zenithal angle. All right, so I have to go up to the elevation angle. And then I have to move in azimuth until I find the satellite. So I need two angles to point correctly the antenna, the azimuth and the elevation angle. The simple trigonometry formula will give you, if this is the satellite, this is the center of the Earth, this is where your antenna, receiving antenna is, then you have this triangle here, and with respect to the zenith, which is this angle here is the complementary of the elevation, because let's say the local horizontal plane is here. Now you can use some trigonometric relationships, and from the first two you immediately find the elevation angle in terms of the height of the satellite, the radius of the Earth, the range, and the sinus of the direction cosine between your orientation and the satellite. This expression sometimes is also manipulated and written only in terms of the latitude and longitude, and this is what at the end you find. Here you have how to develop and find this formula. For our case, if we want to point a satellite from Barcelona to the Astra at 19.2e satellite, then what we have to do is we have to look south and then you go up from the floor 39.2 degrees. And now you only have to move on the azimuth to get to the satellite. The azimuth angle is found in exactly the same way, but now here the trigonometry, the triangles are spherical. You have two meridians and the equator, 90 degrees on those two angles. This is the longitude, both in the North Pole and also on the equator. And this is the triangle that will help you in the calculation. For spherical triangles, you have that the latitude divided by the sines of, let's say, the sine of the latitude divided by the sine of this angle should be equal to the sine of the longitude, in this case, divided by the sine of this angle, which is 180 degrees minus the azimuth. And also you have that the sinus of the cosine, direction cosine, is also related to the sinus of 90 degrees, to the sine of 90 degrees. At the end, you get that the azimuth is just the ratio of those two sine functions. And you can also write this in terms of latitude and longitude, and at the end, this is the expression you get. And now to finish, let me tell you something. Normally, the azimuth angle is always given from the north, rotating on the horizontal plane. You start from the north. In this case, if I'm looking south, the north is behind me. So I start to move from the north, then I do it clockwise. So I go in this way. That's the way I go. For you, it will be on the other, on the other direction, as you see. And that means that what I have to do now is I have to go up in elevation, and now I have to move and point to 155.2 degrees and looking in the southeast direction. If I do this, now I'm just pointing to the satellite and I'm ready to receive the signals from them.